Okay, picture this. You're cruising down the highway, music playing, and suddenly the massive truck right in front of you just slams on its brakes. How much distance should you have maintained to avoid a totally catastrophic collision? Well, it's a split-second scenario, right? But it relies entirely on the invisible rules governing our physical world.
Welcome to this explainer. Today, we're going to demystify the foundation of how things move. Everything in nature is in motion, from massive astronomical objects down to those tiny dancing dust particles in a sunbeam. But if we really want to animate all things in our minds and understand this chaotic movement, we have to start with the simplest, most elegant form of it, linear motion.
All right, here's our roadmap for today. We're going to cover the world in motion, pinpointing position and direction, distance versus displacement, velocity and acceleration, and we'll wrap up with the equations of motion. Let's dive right into Section 1, the world in motion, exploring the simplest kind of movement. So, I want you to mentally animate this train for a second. Picture it gliding perfectly along a totally straight, endless track. This right here is what we call linear motion, just motion in a straight line. By visualizing movement exactly like this, stripping away all the complex curves and chaotic turns of the real world, we basically create a perfect laboratory to observe the basic laws of physics at play. Moving right along to Section 2, pinpointing position and direction, finding our place on the line. Here's the thing, before we can even begin to measure how fast that train is moving or how far it's gone, we have to lock down exactly where it started. We literally can't know if an object is in motion unless its position changes relative to a fixed spot over time. We call this crucial fixed spot the reference point, or the origin O. You can think of it as the anchor for our entire reality. Without this anchor, talking about motion is kind of meaningless.
Let's animate this idea a bit more. Picture this athlete bursting off the starting line, which is our reference point. As she sprints forward, we say she's moving in a positive direction. But if she were to turn around and run backward past that starting line, she enters negative territory. Just like that compass next to her shows us. Simply knowing that she moved isn't enough. Direction is absolutely essential to pinning down her position on that line.
Which brings us nicely to Section 3, distance versus displacement. Why the path matters.
Okay, these two terms get confused constantly, so let's watch this unfold in our mind's eye to see the massive difference between them. Imagine our athlete sprints all the way from the 0-meter starting line to the 100-meter mark, but then she turns around and jogs back to the 40-meter mark. The total length of the path she actually ran, the physical ground her feet covered, which is the total distance, is 100 meters forward plus 60 meters back. That's 160 meters. But her displacement? That is just the net change from her starting point to her final position. She started at 0, she ended at 40, so her displacement is a mere 40 meters.
Now, I want you to actively solve a quick puzzle with me. Can the total distance traveled and the magnitude of displacement ever be exactly the same? Think about a runner for a second. The answer is yes, but only under one very strict condition. They are only equal if the object moves in a perfectly straight line and absolutely never turns back. The split second she turns around, her total distance keeps climbing, but her displacement starts shrinking.
This distinction actually sets up a bedrock concept for the rest of our journey. Distance is what we call a scalar quantity, meaning it only requires a numerical amount, a magnitude. Displacement, on the other hand, is a vector quantity. It absolutely demands to know both the magnitude and the specific direction you're heading. Grasping this whole vector concept is the perfect launchpad for our next phase, which is measuring speed and acceleration.
All right, Section 4, velocity and acceleration. Time to add some speed and jolts to the mix.
What's really fascinating here is that average velocity is calculated specifically using displacement, not total distance. And because velocity uses displacement, it inherits that vector property we were just talking about. That means when we discuss velocity, we must include a direction. A positive velocity means moving forward relative to our origin, and a negative velocity means moving backward. It's not just about how fast you're going, it is entirely about where you're heading.
Let's bring this textbook physics right back into your own body for a second. Imagine sitting in a car at a red light. The light turns green, the driver floors the gas, and you are immediately thrown back into your seat. Or they suddenly slam on the brakes to avoid that truck from our very first slide, and you jolt violently forward against the seatbelt. That physical, visceral sensation you feel right in your gut, your own body is literally acting as a natural physics instrument, detecting a rapid change in velocity.
That physical feeling, that is acceleration. It is simply the rate of change in velocity over a certain time interval. When the car speeds up, that's positive acceleration, building up the velocity's magnitude. And when you hit those brakes hard, that is negative acceleration, working in the exact opposite direction of your motion. And that leads us to our final part, Section 5, the equations of motion, our mathematical toolkit.
So let's mentally animate the math itself step by step and see how science has built this toolkit for constant acceleration. In step 1, they start with our simple tool for acceleration, arranging it to show that final velocity equals initial velocity plus acceleration times time. In step 2, they beautifully substitute that into the average velocity formula. And then, literally like a master key turning on a lock, step 3 reveals a mastery equation. Final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. This single elegant equation completely links displacement, starting speed, final speed, and acceleration. It basically lets us accurately predict the future of a moving object.
To pull this all together, everything we've covered connects directly back to that real-world train and the runner on the track. To understand motion, you absolutely must anchor it with a fixed reference point. You gotta remember that distance is the sweaty total path you ran, while displacement is purely the net change from where you started. Velocity takes that displacement and tracks it over time, always demanding a direction. Acceleration is that physical, gut-dropping jolt when your velocity changes. And finally, those kinematic equations are the mathematical glue connecting all these variables perfectly together.
I want to leave you with this one final thought. If the actual fuel your car burns depends entirely on the total winding distance you travel, but getting efficiently from point A to point B relies purely on your straight-line displacement, how might mastering these simple kinematics change the way you look at a map when planning your next journey? Think about it the next time you're out there on the road, observing the beautiful, complex world in motion all around you.